Hi, I'm Justin Hensley. I'm a senior member of technical staff in AMD's Office of the CTO, where I work on advanced technology initiatives. This is part 3 in a series of videos about OpenCL. This particular video is going to talk about resource allocation, how you do resource setup and allocate resources and set up the OpenCL runtime. So just a quick review from last time. Let's say we have a single context that's talking to two different devices. In this case, the first device is an ATI GPU, and the second device is a multi-core AMD CPU. So an OpenCL application is pretty simple. You just have to compile code, create data and arguments, and execute that code. Today we're going to really be focusing on the section where we actually talk about memory objects, how we create those memory objects, and also setup of our context and creating of our devices. So let's look at how you would actually set up an OpenCL application. First thing you're going to do is you're going to get the devices. The next thing you're going to do is create a context. And then finally, you're going to create command queues that you'll actually use to talk to these devices. So the first thing we're going to do is actually query our system and find out what kind of devices we actually have. So you notice here we're using two different calls to CL get device IDs. And in the first case, we're saying, give me a GPU device. We're going to tell it, we only want one, and give me a GPU device. In the second call, we're saying, give me a CPU device, and we're only requesting one. So in this simple example, we're creating one OpenCL device that'll talk to an ATI GPU, one OpenCL device that'll talk to an AMD multi-core CPU. But they're going to be in the same shared context so they can actually share data. So we have this context, and the way we create this context is with the CL create context call. You note we pass in the devices, the device list that we created in the previous set of code, and we tell it two, because we're creating a context with two different devices. The rest of the arguments are the defaults. Finally, after we've created this context, we actually have to have some command queues to allow us to talk to these devices. And as I was saying before, we have to have a single command queue, at least a single command queue for each device in the system. So in this case, we're going to be creating two command queues to talk to the two different devices we have. So in the first time we call CL create command queue, we pass it the context that we care about, and then this particular device that we're talking about. In this case, we're going to return a value that we're going to call queue_GPU to let us know that this is the queue associated with the GPU. And the second time we call CL create command queue, we're passing in, again, the same shared context, but this time we're passing it a different device. This is the device for the CPU, and we're going to denote that by saying that this queue is the queue_CPU, so we can keep track of which queue is for which device. So some quick notes about setup. Multiple cores of a CPU are considered one OpenCL device. So even though, let's say we have a multi-core CPU that has 6 cores in it, we can actually treat that as one OpenCL device. So OpenCL is going to execute the kernel across all the cores in a parallel manner. So if you have a system with 24 cores, so let's say you have a 4-core Istanbul system, then all 24 cores are going to be used by OpenCL. Your context enables you to share memory objects between devices. So to share data between devices, both devices must be in the same context. If you create the devices in separate contexts, they will not be able to share data. Finally, with queues, all work for OpenCL is submitted through queues. That is the only way to submit work to your OpenCL devices is through queues. Each device must have a queue. You can actually have multiple queues pointing to the same device, but you at least have to have one queue pointing to a device to actually use it. So choosing devices. So a system may have several devices. Which is best? So that's something when you're looking at your system and you see that it actually has one or more GPUs and several multi-core CPUs in it, you have to decide what is the best device to use. So the best device is actually algorithm and hardware dependent. So how do you actually figure out what is the best device for your algorithm? Well, you can query the OpenCL runtime for device info with the CL get device info call. And with that, you pass in basically a device that you want to query, the parameter name, and it returns the value and the value parameter. So you could ask, how many compute units does this device have? What's the clock frequency? What's the memory size? Or even what extensions that device supports? Because depending on which extensions are supported, that will change which device you might want to use. So you should pick the best device for your algorithm. So that what I'm saying here is that sometimes the CPU is better and sometimes the GPU is better. It'll just depend on the algorithm that you're implementing. And you shouldn't feel that you have to use a GPU just because it's there, or you have to use the CPU just because it's there. You should use the best device for what you're trying to implement. So let's talk about some memory resources. So there are two basic types of memory resources in OpenCL. The first are buffers. These are basically simple chunks of memory. So if you're used to programming in C, it's just basically a C array. And that's actually how you access it in an OpenCL kernel, is to use the array syntax with the brackets. The second type of resource are images. So these are opaque 2D and 3D formatted data structures. So again, if you've done any OpenCL programming, this is going to be very similar to a 2D texture or a 3D texture. One thing that's very special about images in OpenCL is that you must access images via the read image and write image calls. And each image can be written to or read from in a kernel, but not both at the same time. So in a single kernel call, you can read from an image or you can write to an image, but you can't do both in the same kernel call. So let's talk a little bit about image formats and samplers. So one of the nice things about images is that they have a defined structure. So we need to actually know what that structure is. So the first part of that structure is what's the format of the data. So how many channels and what's the order of the channels. So that is it an alpha channel? Is it a red-green channel? Is it a 4-channel image with red, green, blue, and alpha? There's a rather verbose set of these, and I recommend that you look at the spec to see all of the details of what can be expressed in OpenCL. There's also the channel data type. So it could be something such as float, int, etc. So you use the CL get supported image formats call to actually tell you what are the supported formats. So besides the format and the type of the image, you also need to know the sampler. And that's for when you read from data, you need to know how to sample the data from the image. So there are 3 basic sampler data points that you need to know. The first is the filter mode. Are you doing linear interpolation or nearest neighbor interpolation? The next would be the addressing mode. So how do you address data when you access outside the image? And the final is, are you using normalized or unnormalized image coordinates? So are you accessing the image between 0 and 1, or are you using integer locations inside the image? So the reason that you want these special image objects is that it's going to benefit from special image access hardware that's built into things such as GPUs. GPUs have very fast special purpose hardware designed to do this filtering, addressing, and handling normalized coordinates in real time. So if it's there, you might as well use it if it fits your problem. So let's see how we would actually allocate some images and buffers. So the first thing we need to do is actually declare the type and format of the image buffer. So in this case, our data type is set to CL float because we're dealing with floating point data. And the channel order has been set to RGBA, so red, green, blue, alpha. So it's a 4-channel image that we're dealing with. So after we've set our format, we're going to actually create 2 2D image buffers. So we have to, of course, give it a context because your data has to be associated with a context. The next thing we're going to do is we're going to pass in the format. So we're telling the allocation routine what's the format of the data. The next thing we're going to do is we're going to tell it the actual size. So in this case, it's image width and image height because we're allocating 2D images. So after we've called it twice, we have 2 image objects, one called input image and one called output image. So now let's create the other type of memory object, which is called a buffer. So in this case, we're going to call the CL create buffer call. Again, we're going to pass in the context because the runtime needs to know what context to associate this memory object with. The next thing we're going to do is pass in the size of this buffer in bytes. So in this case, we pass in size of float times width times height because we're allocating in bytes and we need to know the bytes. Again, you'll note we don't tell it the format of the data because this is just raw chunks of memory. So we don't need to know whether it's floating point data, integer data, or even a piece of a structure. We just need to know the number of bytes to allocate. And after we call it twice, we'll have a buffer for input data and a buffer for output data. So now that we've actually created these memory objects, we actually need to be able to get data into and out of these memory objects. So there are special calls in OpenCL for reading and writing memory object data. But let's say we want to read data from a region in a memory object and actually put it in host memory. So what we're going to use is the CL enqueue read buffer command. One quick note here, we're enqueuing this into our command queue. So the first argument is going to be which queue are we actually doing this enqueue operation. The next argument is the actual object we want to do the read from. The third argument is whether this is a blocking call or not. The next argument is the offset into this memory, and then the size. There's an equivalent write to a region of memory object from host memory call, and that is conveniently named CL enqueue write buffer. And it's going to take very similar arguments to the read buffer, except that the direction that it moves data is the exact opposite. So whereas read buffer takes data from a memory object and places it in memory, write takes memory data from host memory and puts it into a memory object. Another option is, let's say we want to map a region of memory in a memory object to the host address space. So with that, what we're going to do is we're going to enqueue map buffer. And so what that allows us to do is directly access the data that would be used in that memory object. So we could actually one by one go through and change the data. Note, this might not be the most efficient way of doing things. It'll depend on the runtime and the particular application that you're writing. You can also copy regions of memory between 2 memory objects. And you use the CL enqueue copy buffer. And so that takes a queue, a source object, a destination object, and 2 offset parameters. So it's key to note, again, that there is no context passed to this because we can only share data with memory objects that are allocated within the same context. Also, they all operate asynchronously or synchronously depending on whether the blocking call is set to CL true. If you set the blocking equal to CL true, then they operate in a synchronous mode, which means that they will block until the actual memory operation takes place. And this can actually take a fair amount of time to transmit the data depending on where the memory is being copied to and from. Alternatively, if you pass in CL false to that call, it'll be an asynchronous call, and that call will be enqueued into the runtime, and you'll have to use the OpenCL event management system to actually guarantee that the memory has been copied completely before you actually use it. My name is Justin Hensley, and I'm a senior member of technical staff in AMD's Office of the CTO. Thank you for watching this video.